Thanks for joining the session. We'll be now starting the presentation for the demo. So a big thank you to our partners here, Ciclu, Nextworks, Accelera, Nubificus, Mellanox, and of course ICCS. Dimitri, thank you for being here. Just for reality check, we are at the end of this roadmap. So we are at month 48, and after all these delivered tasks, we'll be now delivering the last one, task 6.4, which is actually the demonstration. For this demonstration, we have integrated a lot of cutting-edge technologies that were provided by our partners, but as well as some in-house solutions developed by the University of Bristol. To begin with, we do have the TSON in our transport network. So we have a multi-level programmability and on-demand encryption. So we provide transport layer and security for the 5G complete platform. We have also integrated the millimeter wave mesh network at the midhole, which is also integrated to the orchestration developed by Nextworks, and we can automatically control the millimeter wave links. At the same time, we did integrate the ORAN solution from Accelera, and it is also integrated to the orchestration, so we can have a dynamic RAM management, and by doing so, we can achieve the required energy efficiency in the 5G run. The MEC is also integrated. We have deployed a couple of applications on the MEC node, which is also integrated with the Nextworks so that we can dynamically instantiate and deploy the different applications. The objective of this demo is, of course, to demonstrate all of these technologies provided by our partners and showcase this in the umbrella, let's say, of future cellular networks use cases. For example, the augmented reality and virtual reality use cases, mixed reality use cases, and high-resolution media services. Our testbed consists at the moment of 2 cell edges. Both of them are located at MSHED Museum because we had some unforeseen circumstances with a curious site. We have 2 cells, 5G cells, at each of the building edges. So we have one edge and cell site at the west and one at the east rooftops. All of the computational capability and the DUs are collocated in the IT room on the first floor of the building. So later on, the on-site demo will take place at this location. So we'll have some live feed from the site, and you can see the sites on a, let's say, more closer look that we'll be using our phones to show that. For the architecture of the 5G complete demo, we considered, let's say, multiple deployments that we could have with let's say, the disaggregated 5G core and the ORAN architecture. However, taking into consideration the capability of the solutions that we had, we chose to have the DU at the edge and the CU at the, let's say, the cloud and the core network here in MVP. So we have the RU on the MSHED rooftop. We have the DU in the MSHED IT room first floor. And the CU is instantiated here in the University of Bristol premises where our cloud network is located. So in order to have this data breakout, let's say, so the user data travels through the UCU and the UPF, and we have the MEC node directly attached to the UPF, let's say, subnet, so we can reduce the in-between, let's say, hops and latency. So this is the complete network design. We showcase different edges and our central cloud network. So on top, you can see our central cloud network where we have our 5G core and also the different components and the technologies that we integrated for this demo. So we have the MEC node from Nubificus and the GPU capability from Mellanox. We do have the RIC and the CU from Accelera, the orchestration from Nextworks, and the corresponding SDN controllers for the TSON, the MEC node, and the millimeter wave mesh network. So we use our, let's say, dedicated fiber across Bristol to connect cloud network to one of the edges. So we are not using any, let's say, layer 2 capability to connect these 2 sites. We are using the TSON that was developed by the university. So anything that travels between, let's say, the Smart Internet Lab and the edges goes through the TSON and is encrypted dynamically. From there on the edge 2, as you can see on the bottom, we do have the other end of the TSON solution, which is connected to the millimeter wave hub, the central millimeter wave access point, and the 5G O-RAN components that are allocated to that edge. On the bottom left side, you can see the other, let's say, edge where it's not connected using any fiber to the rest of the network. We are using the millimeter wave mesh to provide, let's say, the transport, the mid-haul connectivity between this side and the rest of the network. And we also have other O-RAN components as well as another cell, 5G cell that we can use to provide the end users with services. Between the cells, the users can travel from one edge to the other, so from one cell to the other. And we have fully configured the inter-DU handover to facilitate this movement. So the previous slide was the relatively simple, let's say, design of the network. In this slide, I decided to show this slide just to show that things are not as easily implemented as shown in the initial designs. So here you can see where each of the components are located. So we have the different edges and the HPN where the central cloud is located. But also between the edges, you can see that there is some collocation of the components, and there was a high complexity in the, let's say, architecture design in order to achieve this. At the same time, given the millimeter wave and the TSON tests that we've been running, we also had a secondary, let's say, wire network deployed between the different components. So in case we lost access to the different, let's say, wireless mid-haul and TSON paths, then we could just access our devices through the wired network. At the moment, this network is only used for device management and for nothing else. The whole implementation, the orchestration communication, the data and control plane of the 5G and the application services are all running on the black, let's say, lines through the TSON and through the millimeter wave mid-haul. For today's demonstration, we'll have basically two parts. One is, of course, this presentation that will include some demonstration of the TSON. So we will have some parts of the demonstration during this presentation and it will be more TSON focused. We do have a 5G CPE installed to one of the cell sites at MSHED so that we can showcase the end-to-end TSON deployment and the reconfigurability over the 5G O-RAN. After we finish this presentation, we'll travel to MSHED with a few phones, of course, demonstrate the whole end-to-end service provision through the orchestrator, and the orchestrator will basically instantiate and reconfigure the 5G RAN. It will control and provision the millimeter wave mid-haul and also instantiate and deploy the secure MEC and the applications on board. So now I'm going to pass this presentation to Romerson.
All right. Thank you. Thank you, Konstantinos. Yeah, so from this point, we're going to talk a little bit about the TSON implementation. From the last meeting, we had a lot of development around TSON, mostly on the synchronization methods and on the aggregation, the encryption, as well on resiliency. And I would just like to highlight at the beginning some results from the synchronization, because we were using time to digital conversion between the endpoints. So we could achieve a very high precision of 21.2 picoseconds when we had two nodes distributed in a network. And this was published this year as a result of these investigations for 5G Complete. As you can see on the right-hand side of the slide, we have the time synchronizer core, which is TDC-based, implemented in the FPGA, alongside with the network control and the encryption control for the time-shared optical network. And here, just to highlight the traffic aggregation capability of TSON and the on-demand for the secure links, which is actually the target of this demo today. We're going to focus on how we can change on demand the encryption schemes based on requirements such as latency for each core, algorithms that are highest consuming in terms of time complexity inside the FPGA. So based on this, we can change on demand and see that the connectivity still goes on, and also play with a little bit with the 100G link, which actually we had some resilient links on the 10G as well, and this is all deployed on the TSON for today. At this point, for now, we bring the SDN controller integrated with orchestrator. This will be demonstrated as well. And I would like permission to share my screen for a bit so I can show what is the site of TSON deployment today. This is here where we are right now. We have the TSON deployed in our lab. So this is actually where we have both TSON nodes. These servers on the right-hand side, each one of them hosts one FPGA card with one edge node of TSON deployed on it. Also, the SDN controller is distributed among these nodes. On the left side there, we have two FPGAs. If you can see here, they were used for the synchronization scheme, but they are integrated, so all FPGAs, they have the same core implemented, but for today, we're focusing on the time sharing of the aggregation capability and the on-demand encryption capability. So these fibers that they arrive here to TSON, they come from the endpoints that are on different sites, and this is exactly what is going to be the source of our traffic later on today. On top of that, we can see here the control from the response to the orchestrator. And here, this is how we're gonna control the changes on TSON. So we can see, for example, that everything is connected now. We can talk to the controller. We can talk to the orchestrator. Yeah, and as soon as we proceed to the demo time, then we're gonna come back to the reconfiguration of TSON on demand, and then we show connectivity still going on. Now I hand back to you, Konstantinos. Thank you.
Okay. As a starting point, we'll have some pre-onboarded network slice and the corresponding subnets. And we'll instantiate the end-to-end services and have them deployed basically in our network. In order to instantiate these end-to-end services, we first need to instantiate the RAN, CU and DU, and configure the RAN as well. We'll have to provision the TSON and the millimeter wave parts of the network. And we also need to deploy the applications in the MEC node. Then we'll have a live presentation of the infrastructure controllers and how they work, as well as the orchestrator. After that, we'll continue with the demonstration of the verticals. So we'll go to MSHED and we'll have the end users, which will be 5G devices, moving between the edges and running the different applications that were instantiated on the MEC node. We'll continue with the dynamic DU deployment and reconfiguration using the orchestrator and the accelerator solutions. And then we'll trigger the RAN reconfiguration through the orchestrator. Okay, go ahead, Ella.
Yes, hi, Konstantinos. Okay, so here we can see the topology which is implemented in this demo. We have on the right, we can see the mesh node. And on the left, we have two terminal units. In the demo, we will have two configurations. We will use first what we call NCF1, the configuration 1, at which a single terminal is connected to the mesh node. Then we will break this link and we will show that the system is reconfigured with the second network configuration file, connecting the second terminal node. Okay, here on the left, we can see the flow of the millimeter wave SDN controller. The flowchart of the SDN controller, we have the Windy, which is the offline network planning tool. The network plan is based on the network requirements, which is the required coverage, the cost of this dealing with the interferences, and of course the location of the actual fiber port. The Windy tool is generating the network configuration file. It can generate more than one, as we have in this demo, for different scenarios. The network configuration file is driven to the runner, and the runner is actually configuring the entire network, layer by layer, going from a mesh node to a mesh node in the different layers of the entire network. On the right, we can see the flow of the controls. At the beginning, the runner configures NCF1, which is the first network configuration. Once the system is fully configured, the runner is performing calling, checking the validity of the configuration. Once it sends a failure, it creates a call for the orchestrator. And the orchestrator sends the second configuration file, and the runner is reconfiguring the system based on the second configuration, overcoming the failure.
Now, this is Juan from Nextworks. I will focus on the part that it has been, let's say, included in this demonstration for the orchestration part, highlighting which were the new functionalities with respect to the previous demos. First of all, we are focusing again in this instantiation of the end-to-end slice for the gaming and streaming applications. And in this scenario, we cover the deployment of the run, covering the deployment of the CUs that we demonstrated in previous scenarios, but in this case, we enhanced the workflow to include the configuration and the activation of the views, depending on the coverage area that we need to use. Then we also include the part of which was not covered. So we have to develop a new model that interacts with the Tyson controller from the University of Bristol to allocate and provision the connectivity based on the service requirements. And of course, in this case, we have two new applications that are in a similar manner as we did in some demos before. We triggered the instantiation of these applications through OSM into the Met from meeting. Okay. The main part, or from our perspective, one of the key features that we want to demonstrate is that we can dynamically activate or deactivate the views based on the user demands and the metrics that we can, in principle, obtain from the infrastructure, as we will see also during the demo. So basically, at some point, we can enable external software controlling the network to actually accommodate the resources needed for the particular user demands through APIs. So this could be enable the allocation of views based on, as I said, in different metrics that we can extract from the service, from the infrastructure. This required us, as you can see in the picture, some modifications on the software that we had or that we demonstrated in the previous demos. So first of all, we updated the API that we exposed toward the northbound to enable this run coverage update. This had, of course, some implications internally in the models that we have internally at the network slice management function. So we have to modify our network slice instance LC manager, and of course our clients towards the run. Then we also included, as I said, for this scenario, although we had some initial developments, but integrated with our development, we included the Tyson network slice subnet management function, which allows provision transport connectivity using Tyson, mainly using, let's say, relying on the configuration parameters that the Tyson control exposes, which are the bandwidth, the crucial scheme, and so on.
Regarding the MEC node, we actually built the custom system stack that enables secure and efficient execution of workloads. So the key innovation point of our contribution to this project is that we built a root of trust so we can attest the deployed applications. So we have secure boot on the MEC node, a trusted way to execute applications on the MEC node in terms of either of the operator. We have enabled multi-tenant use through sandboxing the application itself. This is another layer of security against malicious, maybe users that would be able to execute on the MEC node. We also have enabled efficient execution. We're able to reduce the CPU and memory footprint by the use of unikernels. This is not showcased in this demo, but we have individual demo videos that we can show that. We also enabled the flexible hardware acceleration through our VXL framework. And finally, we glue all these things together to provide an efficient and secure function as a service framework for the edge, also showcased in the video. What I would like to show you a bit is the already instantiated functions that we have here at the demo at the site, how these are being attested, so how we enable the trusted execution on the MEC node. This is actually, there are two parts. The first part is that we should ensure that the MEC node is running what we expect that it's running. So it's running our own system stack. It's booted through secure boot and runs our kernel. And the second part is that the application that is being deployed through the Nextworks orchestrator is the one that the operator, let's say, the application developer, the application provider has provided to the operator. So what we are supposed to run on the Mac node is actually running on the Mac. Let me just share my screen. So I think 1 minute. Let me see my screen. This is, we are already logged in to the Mac node. So let me just, so it's running our own kernel. A custom kernel, it's our architecture. You can see that there are 12 cores, there are 32 gigs of memory, and the NVIDIA R35 release. So in this node, we have installed Kubernetes as the local orchestrator, and this is the part that interacts with the Nextworks orchestrator. At the moment, we have instantiated 2 applications, the ones that we will show in the live demo shortly. And we can interact with the cluster and see the applications running on their own namespace. The notion of an isolated container in Kubernetes. So we see those 2 applications. It's the Minecraft gaming server and the streaming server. These 2 are running. And if we dig in a bit more in the deployment of the application, we can see that they are made of a specific container image. So if we do what it says here is that it pulled a specific image, and this image corresponds to a specific tag. This is a container image. Let me describe the deployment. So this is what comes from the Nextworks orchestrator. This is the instruction spawn this application. So this deployment has as an image this specific tag. This specific tag is built by us, and it's signed using a token of a GitHub action operation. And installing a specific policy on that namespace, we need to go into the namespace specifically, and we need to specify that this namespace where the applications will be deployed or are deployed already has to honor a specific container image specification. This policy is defined by us, and it's defined using these parameters. And these parameters are that the issuer of the signature of this image is github-user-content.com, which is github.com, and it has to match a specific expression, which is this one, and this means that it has to be signed by our workflow of the container image treatment. What we show here is that any other container image not defined by us, that means that it's any other container image that is not signed by our workflow will not be able to be deployed on the Mac. And in the case that someone says, okay, I'll change this policy, you cannot change this policy because this Mac node is booted using secure boot. So you'll have to be a malicious user that is able to exploit the operating system. If you have physical access to the Mac node, which is the attack vector that we protect against, if you have physical access to the Mac node, you cannot alter something. You have to break it. It either works or it doesn't. You cannot spoof that this is a service that you can use so you can get data or passwords or keys or something like that. After this longer part, let me go back to the slide. And this is the part that is going to be showcased along with the next slide, where we enhance this kind of security trust using an isolated execution environment. So we've got at the left side, there's the generic container execution. In the middle, there's the sandbox container execution. And at the end, it's the uniternal execution, which is a combination of both words. And what we use at the demo here in Bristol is the middle one. The applications are spawned as containers, but inside micro VM. This gives an extra layer of security against attacks, more elaborate attacks. On the Mac node, there is a malicious application that needs to get data from this application that we are talking about. This VM protection, this sandbox protects the application and the Mac node from malicious third party. This is not demonstrated in the Bristol demo, but we have some screencasts and videos available at the SharePoint folder to showcase our work on that. So briefly, the rationale is that we enable flexible hardware acceleration through our framework that we developed as part of the project, so that workloads that are running inside use the hardware accelerator enabled on the neck node in an efficient way. We have integrated that with the container runtime, and this all runs smoothly in a cloud-native way. And all these technologies get integrated into a FAS framework. We used to use OpenFAS, and we moved into Knative, which is more generic for Kubernetes deployments. And through Knative, we can spawn functions on heterogeneous clusters like the MEC node and the cloud server that are able to use hardware acceleration through the Accel and that are secure enough to be available as a service. The multiple tenants can be able to run functions on the same infrastructure without being afraid that the data will leak or that they will be attacked by malicious third parties that are running on the same node. This is a short screencast of a unikernel being deployed as a function, in a function as a service on an x86 machine. I'm sure we can skip that. This is available to be shown in the folder with the videos and all that.
So the RAN in 5G Complete. So in Lanyon, we demonstrated aspects of the RAN, where we showed we had an indoor deployment, a simple indoor deployment where we were running over the PON and the point-to-point fiber with the P2P running. In Bristol, we're extending this, so we have an outdoor deployment of 2 cells which are configured dynamically. So it's configured as a standalone non-public network. It's fully compliant with 3GPP standalone, but also has the disaggregated Open RAN or ORAN additions, such as the RAN Intelligent Controller. So we will be demonstrating the full orchestration of the RAN, starting from the CU, both the CU-CPC and CU-UP, and then instantiating the DU instances and dynamically being able to control those. And as mentioned as well, we will also be running the cross-haul of the RAN over the optical technologies that are being shown, the TSON and millimeter wave. So what we will also be showing, and which was funded as part of 5G Complete, were things like the mobility, the standard mobility between cells and the dynamic control of the cells. We were asked in the last review meeting in Bristol to demonstrate something more dynamic, to show aspects of the capabilities of what the orchestrator can do and what the RAN can do in a more dynamic environment. And the use case we've chosen for this is RAN energy efficiency. Now, this is not something that has been identified as a use case within 5G Complete, and indeed is being researched intensively in many SNS projects. So we don't intend to provide a very mature use case, but we're providing some low TRL proof of concept, demonstrating some concepts of how you can dynamically reconfigure and adjust the RAN based on traffic needs and traffic desires. So you've seen this figure before, I think. So what we're deploying here, we have the RIC and the CU provided by Acceleran, and we've integrated third-party DUs. So there's 2 DUs, each connected to an RU. We're integrating to the 5G core that we have running, an open source core in this instance, with a separation of UPS being able to logically deploy UPF in the MEC or in the central core. And we're also integrating northbound with the SMO for the Nextworks orchestrator in Mano to be able to deploy and configure and provision the RAN. As this energy efficiency use case is new, just putting it into context very briefly. Traditionally, 3GPP was mostly concerned on battery life in the UE so that your smartphones last longer between plugging them in. But since about release 16, there's been an increased focus on energy efficiency of the network itself, and the RAN in specific, because it's the RAN that uses most of the energy. And this is an increased in importance in release 17 and 18. And now, as we see, if we move on to release 19, there are, again, additional focuses on network energy savings, and even things like these native AI ML for NG-RAN. One of the use cases of that is energy efficiency. So industry-wide energy efficiency in the RAN is becoming very important and very vital, which is why we wanted to add this to our demonstration. Now, energy efficiency is actually a very broad subject. It's going on in equipment level, the usage of more efficient power amplifiers, all the processors, the latest generation of CPUs have sleep states and have more efficiency. The ARM processors that we're showing in the MEC as well have great energy savings. There's a lot of discussions and arguments about plug-in accelerators for offloading certain functionality that works better in FPGAs or things like that. In the platform itself, some of the things we've actually implemented and are part of the demonstration are kernel bypass techniques to really optimize using standard off-the-shelf servers using XTP. But there's a lot of other things going on. And 3GPP itself in 5G New Radio, a lot of the design criteria with these lean carrier design and allowing the RAN to go to sleep, micro sleep states for longer and deeper. All these are part of standard 3GPP technologies. But where O-RAN comes in is the ability to add intelligence, to automate things, and to allow you to optimize and do more than just to complement what is done on a equipment level. And that's something that we're just demonstrating, taking advantage of the O-RAN RIC and the SMO to be able to do a little bit more. So the use case, the general concept of the use case is a use case that I think is probably the best understood. The idea is based around having always-on coverage cells. So you have a static cell, typically would be low frequency for very broad penetration, indoor penetration. And then you have dynamic capacity cells. Now, in many cases, this would be of higher frequencies that have shorter penetration but higher capabilities. But due to the constraints of the licensing, we're actually demonstrating it on the same frequencies, but allowing additional cells to be switched on and off as we need them based on traffic demands. Now, the savings, typically, there's sort of something between 10 and 20% savings can be achieved in these sorts of use cases. It's based on the idea that in some types of cells, say in urban areas, you have peaks in the morning and evening, but during the day, there's less traffic. And in suburban areas, it's during the normal working hours, there's a lot of demands. But there's actually a lot of complications to this. The fact that cells can take a long time to start. With COVID, that people start working from home, so traffic profiles change. And so these open loop things where you just program times, switch things off at certain times, come back on at certain times, don't really work very well. So you need to close the loop by measuring what's really going on, real traffic demands, and then using intelligence to then automatically switch things on and switch things off. And these use cases go beyond public networks. Of course, in urban areas, these things make sense in quiet times. But it's also very suited to private networks. If you think, say, of a sports stadium, when there's a football game going on, you need as much capacity as you can. When there's no game, just for security and maintenance stuff, and you switch things off. And again, with factories and many other things, when there are no shifts active. So that's the general context of what we will be displaying. And you will see in the demonstrating, we will explain exactly which parts of the thing we're demonstrating. So we're measuring what's going on. We're measuring the RSIPs, the RF performance of users as they migrate. We are then using the signaling to the MANO to be able to switch on or switch off DUs, depending on whether we need the extra capacity or we could save energy. And we're also monitoring the platforms that are being used to show the reduced CPU usage, the reduced memory usage, such that logically those things can be powered down or go into sleep state when they're not used and saving power.
I think this is all we have for our presentation. I will now move on to the more, let's say, practical demonstration of the 5G Complete platform. So I will personally move to travel to MShed with Dimitris. Okay, almost we can go ahead with the presentation of the official deployment.
Okay, so Konstantinos is there with the application, with the endpoint. And now we are running the system with encrypted link on AES with 256. And we're going to change the encryption scheme here and see the impact on the application. Konstantinos is there.
Yes, guys, as you can see, I'm here on site. I have the demo camera set up, and you can see my laptop screen. So you can see that this is the call. And now I'm switching to the 5GCP that is currently set up and is connected to one of the cells that we will be demonstrating later in a few minutes, basically.
I don't know if in the recording it will be possible to show this
here. Okay. So I will change the encryption scheme now. So now we're running, as I told you, we're running AES-256. We're going to put AES-128 variation, and I'm going to see the impact there.
I'm sorry for interrupting.
Yeah.
As you can see from the demo camera, the 5GCP is currently come to one of the cells here in MShed. Here are the connection, let's say, location info and cell info. And I'm going to run a ping test. So I'm going to send packets every 80 milliseconds to our testing VM. It's in the cloud. So I'm going to start pinging now. So I'm going to start the ping test.
All right.
As you can see, we can see the packets being sent and received.
So I will change.
Emerson, you can go ahead.
I'll change it here. We're going to see the response on the FPGA agents here on the bottom left towards the right of my screen. Yes. Everything is changed now. Is a new encryption screen up and running. And we can see the response on the camera, demo camera. The system keeps going smoothly.
So do you want me to get the camera closer to the screen?
Yeah, it's fine. Yeah. Okay, great. New encryption scheme is up and running. So I think from this point, we've shown some on-demand reprogrammability in terms of the security side. And yeah, we are completed with the Tisson real-time encryption scheme changing.
Okay, thank you very much, Sean.
Thank you.
We move to the orchestrator now.
So for the second demo that we have done, if you remember, we are going to demonstrate the applications running on top of the application. If you remember the slide we presented before, the precondition is that we onboarded already a network slice template where we are using network slice templates based on the GBP standards. Here I'm presenting the interface of the web GUI of the network orchestrator developed by Nextworks. Actually, you see here the slice that we are using for instantiating our service. It has different network slice subnets, two for the different transports that we have in the underlying infrastructure, one for the run and one for the application. So particularly the first three kind of define the quality of service parameters that we need for the service, and the second one, and the last one for vertical application, defines the service that we will instantiate through OSM. So then, as we said before, for the scope of this demo, we triggered already the instantiation of the service through our orchestrator. And it is possible also to do this on demand. We just wanted to do this basically before to save some time. As you can see here, different network slice subnets were allocated during the instantiation of the service. First, we go through the configuration of the transport network, allocating the millimeter wave connectivity through the runner and the controller by Ciclu. Then we go through the Tisson configuration to allocate the paths inside the infrastructure. If you remember the deployment of the infrastructure that we have. Then we configure the radio access network. In this case, we have two different areas or two different views associated with two different areas that we want to cover. We instantiated this slice and we activated one of the views in order to be able to cover each area where the users are, let's say, using the application or what the users are. And yes, that's it from the orchestrator perspective. I will switch now to Simon to explain what is happening at the Deluxe level.
Okay, as you can see from a high level, we currently have one active cell, and then we have the user, the demo camera connected to that. If we just dive in a little bit deeper, we can see the overview. We have the CUCP that is provisioned and is running. We have the CUUP that is used for connecting to that one running DU. We currently have, you'll see that both the two DU and RU chains have been deployed, but only one of them is currently running. So you see the DU1, RU1 that is currently enabled and is green, and then DU2 and RU2, which is currently disabled, and we will bring that one online a little bit later. So that's the overview of the current RAN configuration.
Yes, the orchestrator has also already triggered the instantiation through OSM, so we have the instances of the Make applications up and running. We can then now switch if you want to see applications, or I want to show something, the application running.
I'm on my way with Claude to the cell site. We'll show you the video streaming running on the phones, while you show the live, let's say, metrics from the system.
This is the Grafana dashboard. So we can also see, let me just log into the Mac node, actually a little bit later, I'm afraid, because I'm already here, but yeah, I'm not sure what's showing.
We are just seeing the pods that are running.
Yeah.
No worries, you can go and see the application running.
You guys see my camera?
Yes, we can see the camera. We can see that there's the streaming application is receiving and transmitting data. This is the live dashboard from the Grafana metrics visualization software that is running on the Mac node. So this is live server-side metrics from the Kubernetes platform running on the Mac node. And if we inspect streaming servers, so we get the logs, let's say, from the Mac application after lots of logs, we can see that this is live clients connecting, disconnecting, and showing video, which I guess Konstantinos is already showing that.
So yes, sorry for the random image that you can see, but now I'm moving from the east side to the west side in order to showcase that the stream does not really perform well, but when the new cell, let's say, is up and running and we can camp on the new cell, then we can improve the throughput performance of the whole 5G network, and we can have a proper streaming on two phones at the same time. So this stream is currently at 40 megabits per second. Just a moment, I think it's buffering. Yes, so as you can see now, we can have a normal video stream coming on the phone. I'm not sure how well you can see it. And we have another phone on the east rooftop streaming at the same time. Yes, Tasso, you can continue. Please go ahead.
Yeah, so the metrics have a little bit of delay because these metrics have to enter into a time series database and then they are visualized. So what we're seeing at the camera that Konstantinos has is 10 or 20 seconds delay at the graph that we're seeing. But I think that the numbers are in parallel. So what the throughput reported by Konstantinos is also reported in these graphs.
Yes, after the sharing, I will show now the activation of the second view. So as I said in the presentation, we enabled the possibility of allocating allocating views on demand in order to save energy, as we discussed before. In this case, this is the API that we expose from the orchestrator, the northbound. As you see here, we have the slice identifier, meaning that I will be modifying this slice, an action type which says I want to update the coverage, and these are the coverage areas that I want to modify. So I can send just this, and this is actually now being processed by the orchestrator, and it will eventually trigger the allocation of the second view in Deluxe. So since in my Postman I have the correct address of the orchestrator, I'm using I'm triggering the same through a script that we have prepared. Okay, basically here. it's the exact same request. So, but in this case, I will have the address. As you can see, this is what I trigger, basically. Okay, same kind of request saying that I need the area 1 and area 2 to be covered in this case. Basically, extend our area of coverage of the service. And now we should be able to see that in Diracs. Diracs dashboard, let me check. Okay, obviously something is not it's not working. And someone from the network sync, can somebody check what is happening?
One, maybe you forgot to pass as a parameter the NSI. ID.
So you've got the ID as the first parameter.
Okay, we need to verify. We need to verify. Here we see that the post to the new configuration was successful. I guess something is not working in the activation of the view for some reason. And I think from the receptor perspective, the command was sent for some reason at the view. This is not currently being processed because I see we still see it as not activated. But
now I see that the U1 is starting to be enabled. The U2, sorry.
yes,
I think it requires sometimes.
Okay, so it took longer than expected. Just okay. No, I activated manually for some reason. It tends to be working. I don't know why. In the original request that we sent from the orchestrator, it did send the let's say the request, but it took longer than.
You should have double timer.
Yeah.
Okay, so now you'll see that the second cell has come up. There's still currently that one, the UE attached to the first cell. And if we start to walk again, now you'll see the handover to the second cell, and from the throughputs will be maintained because the throughput with the coverage, the signal will be better as it migrates to the second cell.
Can you confirm that the UE has been attached to the second view, and Constantine? We are not seeing the camera anymore.
Yes, sorry. I'm heading now to the two cell sites so that you can see, I guess, the video streaming. That's all we can actually demonstrate at the moment. So just give me a few seconds to move to the balcony. Thank you. Okay, so we have two phones, as you can see. I'm not sure what exactly you can see, but I'm trying to show that the 5G icon is there on both phones. Probably you can see it on the Diracs, on the Diracs side there. You can see two more UEs were camped on one of the cells. So we will try to showcase the live video feed on the phones. Let's see if it's running. Carl, can you please take ownership of the live video feed here? So let me check if the stream is okay and up and running. How do we select the server here? We're not quite sure how to. So this one is starting to run the Minecraft server.
So as you can see here, we have the server, the game server running on the Mac, and we are connected over 5G, and we're able to see the server. Now we're gonna join that, and in a moment we are playing through 5G. Oh, we died. Over to our server, to our game server in the Mac, and you can still see we are connected on the 5G network.
Claude, just to interrupt you, it's good to remind people here that we are what we are showing, just to be clear, is that we spawn two applications. Okay, the user there was saying we are provisioning for two resources for two applications. Okay, the first one is the video streaming that's happening in one of the end units, and the second one is a gaming application that is deployed. Both of them are deployed on the Mac. Okay. So this is why we are showing the gaming application on one of the phones, and then the streaming application on the other phone. Okay, just to be clear as to what we are seeing.
Yes, as Dimitris was explaining, here, side to side, we have the streaming server on 5G.
Is the brightness here?
Brightness is full. It's sunny day, sorry for that. So here on 5G, we're running the streaming server on the IP, the dedicated IP for the streaming server, and then we have the game running as well over 5G.
Sorry guys, I had to bring my laptop here just to ensure that everything works fine. But as you can see, we do have the streaming server here running and the game. So at this point, we can actually demonstrate the game, both devices connected to the same game, and they can play together on a, let's say, on a multiplayer mode on the same server, connected either to the same cell. So everything is over the 5G network, and as you can see, the game on the second phone already identifies that there is one more player within the server. So I'm just joining the server. I'm in, and you can see that both phones are now playing in the same game. So we leave this phone here. Hopefully when we get back, it will still be here. So Claude, if you can take my laptop. As you can see, we're currently connected. I don't know how well you can see it. We are currently connected to one of the cells. So PCI 2 with NCI 514. And we'll be moving to the other cell in a bit. Sorry for this. So apparently I am being attacked. We'll be checking now the cell that we are camped on. So let's wait for it to refresh. Okay, as you can see, we are currently changed to PCI 1, NCI 5. I'm not sure if you guys can see this. We're still in the game. So you can see the live video feed coming from the streaming server on the Mac node. So again, we moved from one cell to the other. As you can see, let it refresh, maybe not yet. Yes. Yeah. So we do have a handover now. So we camped on the second DU again, and we're still able to play our video stream.
So now, as you can see from the screen of the project, in the UE has been attached from one of the views and attached to the other one.
Hello from MShed. We are on the east rooftop, and here you can see we have our 5G RAN and our millimeter wave set up from Siglu. So the central, let's say, the BU unit from Siglu is located right here on the top, and we have the two terminal points on the right and on the far end on the left. So this specific 5G cell does not communicate with the rest of the network using fiber. The communication happens only on the millimeter wave mesh. So we have at each instance one of the links active, so that the GNODB can connect back to our network and back to CU and the 5G core. I guess here today we demonstrate two scenarios using two application servers. One is the streaming server that is going to live feed some video, 4K high resolution video at the bitrate of 35 megabits per second to the 5G devices connected to the 5G cells. We're going to show that after the second device starts streaming the video, both devices will have a very hard time to stream properly, as the network performance won't allow that high bitrate for multiple devices. So the second TU is activated so that one of the phones can come on the second cell and get access to a very higher throughput 5G connectivity. The second application we're going to test today is a game server. So we'll have both phones connected to the same server, and we can showcase a multiplayer game. So both devices can log into the game as different users, and they can both see each other within the game. And uninterrupted, let's say, game services can be provided to the end users even by moving from one cell, one edge to the other. Juan, if you want to take over and please explain what you will demonstrate using the orchestrator.
Thanks, Konstantinos. I have this slide just to recap the different steps that we will present during the demonstration. First, we have our starting point with the pre-onboarded network slices that we have on the network orchestrator. And we already have one instance running and deployed. We will show you this instance running on the GUI. Then we will show you on the infrastructure and how it is laid out. In this case, we have provisioned the transport networks, so through the millimeter-wave and the TSON controllers. We have provisioned the radio access connectivity, so we will show the DRAX and how it has been configured with one CU and one DU active. And then we will show open source Mano, and we will show the Kubernetes containers that are running on the MEC platform from Novity. We will go through this again very quickly, and then we will change the focus and show the vertical demonstration running. So we will switch the control to Konstantinos that will be moving around with two cell phones representing the users moving at MShed. And we will see a live stream following the users on the screen. Then, since again the objective of this or the main objective of this scenario is to show the dynamic control and the dynamic reconfiguration of the run, allocating or activating or deactivating the use based on the user movement pattern, in order to save the energy and to demonstrate this energy saving scenario that we commented before. So we will focus on the metrics that we can obtain from the 5G core and from the views. So we will show the Grafana panels of the 5G core and 5G and the views with the metrics that we can retrieve from our infrastructure, and we also show how the applications are consuming bandwidth and are actually streaming and using the services of the gaming application, and how this affects our infrastructure. At some point, we will trigger the run reconfiguration. We will use Postman for this. We will show you the Postman request that we issue and how we expose this service through the northbound API of the network orchestrator. We will see that this triggers a consequent reconfiguration of the run, and we will see that the second view that has been provisioned becomes active to serve new users closer to that radio unit. And we will show again the panels of Grafana and that with the metrics that we can retrieve from the 5G core and the views. And the main objectives of this scenario, as we mentioned before, will be to show how this dynamicity can be achieved through specialized APIs that we have developed within the project, and in this case, as I said, we will focus on the activation and the activation of the use based on the user movement. This is the GUI interface of our orchestrator. Let me just first show you that we have pre-onboarded a network slice template on our catalog. This is a network slice template that describes the quality of service parameters that we need the network to fulfill. Mainly, you can see that this end-to-end network slice is composed by 4 different network subnets, 2 for the different transport segments that we need, 1 for the RAN, and 1 for the vertical application. The first 3, as I said, determine the quality of service parameters and the requirements of the service in terms of resources. The 4th one mainly identifies the service that we want to run, which in this case contains 2 VNFs, which are the streaming application and the gaming application that we will go through OSM. As you can see, we have already instantiated this network application. This means that the orchestrator has already triggered the configuration of the transport network, firstly, through the TSON and millimeter wave controllers developed by the project. In this case, and compared with previous scenarios, we included the part of the TSON controller which was not available or not demonstrated before. We allocated this and we configured the TSON controller using a certain bandwidth and certain encryption schemes, as was also demonstrated in the loud demonstration earlier. And then we configured the radio access network, deploying the CUs, and activating one of the views that are of the two that we have available at the current deployment. So I will switch now so that we can see the run and how this has been configured and the current situation after the instantiation.
So you see currently we have one cell on there and there's a user equipment attached to it. If we go into more detail of what is there, the single CU CP is up and running. There's a CU UP for the running slice, and that is connected to the running DU. You will see that both DU chains have been instantiated. So the DU and RU1 chain is up and running. The DU2 and RU2 has been provisioned, but is not yet enabled. And that's the dynamic demonstration that we will show later on.
The orchestrator has also triggered the provision of the application, as we will see later in the MEP node. This means that the orchestrator triggered through OSM the instantiation of one network service, which will be allocated through a special beam that we configured. As you can see here, we can see the network service instance is up and running with 2 VNF instances, one for the streaming application and one for the Minecraft server, which is the gaming application. Now I will pass the control to Tassos to present the containers running in there.
Let me just show you quick that we've got. This is a single node Kubernetes cluster, as mentioned before. This is the beam for the OSM. It's the MEC node, essentially running the latest kernel version and the latest container build. So our system stack, essentially. So the containers that are instantiated as part of a Nextworks orchestrator are in this namespace. So we can inspect the pods. There are 2 pods, meaning 2 containers. There's the mining server and the streaming server. And if you see the naming of these components, these are network functions, essentially application functions, instantiated to OSM. They've got local IP addresses and load balancer IP addresses as services. If we can see pods, services, and these are the IP addresses that the user equipment is using to access the relevant services. We can also get a quick look at the logs. So this is the mining server. So there are These are the logs of the mining server ready to serve requests, and logs for the streaming server application, again ready to serve requests.
We can pass now the control to Konstantinos so that you can actually see the applications up and running and follow what an actual user will do.
So we are currently on the west side of MSHED. As you can see, this is our setup on the west side. This is our 5G RAN. Here you can see my colleague Claude setting up the phones. So we are currently going to demonstrate the streaming server, the live video feed to the end users. So the phones are both currently camped on the west edge. I'm not sure if you can see, but you can see some stuttering on the screen. This is because the video bitrate is very high. So when both streams are up and running on both devices, the throughput of this single cell is not enough to provide services to both phones. So at this point, we need to deploy the second DU, and we'll walk around the balcony to camp with one of the phones to the other cell and show that we can have both phones streaming without any issues when the second cell is up.
So now you can see in the screen the Grafana panels that are actually monitoring the bytes that we received and we transmit in the MEC nodes. As you can see, there are some peaks, and we can also show the metrics that we extract from the 5G core and the data rates that you can see here. And we can also show the metrics that we retrieve from the view.
And you can see the difference in the two cells. So the active cell is using a lot more of the performance, and there's a much higher load. And the inactive cell is lower load, which equates to lower energy consumption.
Okay, so now what we're going to do is we will use the network orchestrator API. Using this request that you see in the screen, basically we will tell the orchestrator to extend the coverage area from just area 1 to area 1 and area 2. This is especially a message that we will send. This is a network slice identifier. And we are setting up an action type of update coverage. You can send this. So now what we are going to do is we will trigger the activation of the second view through this new normal interface that the network orchestrator offers. As we said before, we added some normal configuration APIs that enable external applications to reconfigure the network to add more coverage area, basically activating all the activating views. In this case, what we are going to do is we will use this temporal API to add one coverage area, which will trigger, this will be done through the orchestrator, and it will trigger the reconfiguration of the runs, the DDAX, basically activating the second view that we saw before. As you can see in the screen, I have Postman open. And this is basically the message that we need to pass to orchestrator to add the second coverage area. This is the identifier of the slice we created before for the application. We set the action types to update coverage, and we pass the internal identifiers of the areas that we want to cover with this service. Area 1 was already covered. We are just adding area 2 in this case. So I can just trigger this. I get an ID of the operation. And now, if you go to the DDAX configuration, as you can see, the second view has been activated. And now when the users move around, they will be attached to this new view that we have created. At the moment, as you can see, all the views were attached, all the terminals were attached to the previous view. Now, when they will stop moving, we will get better traffic, better traffic data rates, and more bounded for each terminal.
Okay, so now we are on the west side of the rooftop. We have the two phones camped on the west cell. And we can see that there is some stuttering and a low quality, let's say, experience from the user side because two high bitrate videos are trying to stream at the same time on two different devices. So my colleague Claude and I will now move from the west side to the east side so that we can actually camp on the east cell. So switch from the west cell to the east, from edge 1 to edge 2, and by doing so, we can provide the UIs with a higher throughput link, so that both links, both streams can be, let's say, downloaded to the phone without any issues. So Claude, go ahead. I'll be right behind you. So Juan, if you can show the UI camping from one cell to the other, so you can show this transition.
I think Konstantinos, as you can see here, we can actually see that the U has moved and has been attached to the view that we just updated.
Yeah, so the handover has now occurred, and as you see from the phone, we'll get then the whole bandwidth from that cell and be able to stream without interference.
So yes, the handover has been successful. We can see that on the phone, the stream itself, and also from getting the cell information from the phone, we'll see that we are in fact on the second cell here, and here is the stream, which is now playing at a better quality and rate.
Okay, so if we now look at what's happening on the DU servers, you see that once the second DU is switched on, it's using a lot more memory, so there's a lot less free memory available, which also implies then there are more CPU cores attached and also more energy being used by the DU server, which gives the demonstration of the effect on the energy consumption when you dynamically add or remove the DUs.
So now we will focus also on the metrics that we can extract from the MEC node for the two network applications that we are deploying.
Okay, so as we can see in this Grafana dashboard, this is the graphs for the streaming server. One of the phone is already streaming video. And let's move to the other application, which is the Minecraft server, the gaming server.
So we're currently on the west side of the rooftop. We have, I don't know if you can see anything on the screen.
It's currently night of the game.
But we do have the Minecraft server here running. So it's a bit dark because the game environment now is nighttime. But
that's fine. We can see a change in the metrics here. We can see a small increase in CPU utilization, a small increase in the packets received and bandwidth. I suspect it's because they are changing text and not. The important thing is latency.
So now we can showcase I guess the service continuity when we hand over, and we will go to the east side where we have the other phone currently streaming, and we will enter the game server using the other phone as well, and we can showcase a multiplayer game using two phones being able to, let's say, connect together and play the game at the same time. Claude and I are moving to the west side, right now. You can see probably from the DRAX when the handover will take place. You can see, I don't know if you can see anything on the screen. We're currently recording the screen on the phone so that we can showcase properly the procedure later on. But the game is still running, and soon enough after the handover, there will be no noticeable, let's say, service interruption at all.
As you can see, also just now in the Dirac GUI, we see that the user equipment has successfully performed the handover and was now reattached to the original view. Eventually, we could also trigger the activation of the second view, given that we don't have any more users moving to that area.
So now we have instantiated the game client on the second phone. As you can see, the first one is still in game. It's playing just fine. So we are now going to enter the local, let's say, the server we have here in the Bristol testbed. So we can see that there is also one player in the server. This is the first phone. So we're gonna enter now using the second phone. So I'm not sure what you can see, but we do have both phones on the same server, on the same world, let's say, game world, and they can freely play the game.